Any doubt you have from the last lecture?
No.
Any doubt from the last lecture anyone has? Okay, so let's start today's lecture. In the last lecture, we stopped at trying to represent Fourier series using matrices. And we have said and seen that you can represent Fourier series by using this matrix. If something is unclear, you can just ask it. And so if you notice, this represents k times n, right? So in Fourier series, you have summation ak e to the power j k omega naught n. So you have kn. So these things represents kn. Okay, so this is k basically, and here is your n. So you can represent it like this. Now here n is capital N is 4 because we have 4 coefficients. So you can also simplify this, and after simplifying we get something like this. And you can also get AKs from xn's by using this relationship. This matrix is just the inverse of this matrix. Okay. And we have seen that here the problem is number of operations increases as n square. For example, it has 16 multiplication, which is bad, right? So we want to decrease the number of operations because if n is pretty high, 10,000 or something like that, then we will run into trouble. So there is an opportunity to design an algorithm which solves these equations, but in a much fewer number of operations. And there comes the role of fast Fourier transform, which is the algorithm. In fact, fast Fourier transform is the most used algorithm. Okay, so most of you are computer scientists. So this is an important algorithm that people uses. It's the most used algorithm in the world. So we will like to see how can you simplify or reduce the number of operations. So we are going to discuss that, and the first strategy is let us change some notation because it will ease our explanation. So we have introduced this notation W4 to the power m, which is this signal. Okay. So here important thing is this m represents k times n. Okay. And we can see that because we have 4 here, right? So suppose m is 4. Suppose m is 4. So we have 2 pi by 4 times 4, right? So this is 2 pi, which is same as 0, right? So we can think of this as it is doing modulo 4 operations. For example, if m is 5, then this is also 1, right? This is also 1 because when m was 4, this is anyway same as 0. So m being 5 will be same as 1. So you can understand these things as modulo 4. Just let us see how many multiplications, 16 multiplications again, right? So W4 multiplies with this multiplies with this multiplies with this multiplies with this. So 4 multiplications, and we will do 4 times. So total number of multiplications is 16, and there are 12 additions, right? So 3 additions in each row to get A naught, right? Similarly, you will have in total 12 additions, 4 times 3, 12. Any doubt here? Okay. So till this point we have seen everything, and now let us look at something new. So the strategy is as follows. We are dividing and conquering. This is the fast Fourier transform algorithm that we use. So now let us try to calculate ANs or AKs, whatsoever you want to call them. Let us call them as AK. We will calculate AKs, and the strategy that we will use is, so you have x0, in this case x1, x2 and x3. So we divide this Fourier series or these terms into 2 parts. One is x0, x2, so even part, and x1 and x3. Okay. We are dividing this into 2 parts, even part and odd part. And we will see first what are the terms or how these coefficients are influenced by even part. And we will see how these coefficients are influenced by the odd part. And the strategy is then we will sum these two coefficients. So the coefficients that are coming due to the even part are known as BKs. So even part x0 and x2 will influence my coefficients, right? So those coefficients that come due to even parts are known as BKs, and the coefficients that come due to odd parts are known as CKs. Okay. So now let us look at this. So let us define it like this. So B0, again there are only 2 terms, right? So you have only 2 BKs, and you have only 2 terms in odd part, so you have only 2 coefficients, CKs. Okay. So BK again, because there are 2 things, so it is W2. This period is 2, right? No problem. And this will be Kn. This is 0, n is 0 in this case, or k is 0, whatever. This coefficient is 0, this 0, so this will be 0, 0. This is 1, so this will be 0 times 1, and this will be 1 times 1. Okay, and why 2? Because the number of terms are 2, so period is 2. So B0 and V1, I have written it like this, right? Any confusion? Similarly, the same reasoning, C0 and C1 can also be written like this. Now if you see how many multiplication steps here, total number of multiplication steps. So 2 multiplication steps for this row, 2 multiplication steps for this row, similarly 4 multiplication steps here. So total number of multiplications are 8. Okay. Similarly, you can see, I will not repeat additions again and again. You can also calculate that the number of additional steps is 4. So total number of steps are 12 for calculating B0, B1, C0, C1. Okay.
Sir, why is 2 here, in W2?
Because there are two number of terms, x0 and x2, right? What I am doing is, I originally had 4 terms. I am trying to create a Fourier series just with 2 terms. I will have a Fourier series just by 2 terms. So the period is 2. Okay. Then this will repeat.
Yes, sir.
That's why W2. Any other question? Clear?
Yes, sir.
Okay. Thanks. Now what we are doing is, this is the strategy. So we are saying AK is DK plus EK. Okay. We will see that DK comes from even numbered and EK comes from odd numbered XN. Okay. So AK is DK plus EK. DK is coming from even number and EK is coming from odd number. And AK is sum of DK plus EK. It will be clear once you look at this. So let us now focus on DKs. Okay, just for your ease, I have already shown what are BKs. BKs we have already defined. Okay, so this is like this. Now good point is, I can also translate this W20. I can also write it like W40. Both are same thing because anyway both these things are 1. So W20 is same as W40 because both of these things are 1, right?
Excuse me, sir.
Yes.
There is a factor of 1 by n also, right?
Let us ignore this at the moment because this factor anyway can be incorporated quite easily.
Okay, like we have to multiply that factor only. Right?
So let us just focus on this part at this moment. Of course, there was something here which we are ignoring. Because this is a constant, this can anyway be incorporated in the end. Okay. So W20 is same as W40. This is same as this. W21, if you see this, it is same as W42. Right? If you look at this, e to the power j 2 pi by 2 times 1. This is same as e to the power j 2 pi by 4 times 2. Right? Same. So W21 is same as W42. X0, X2. So earlier I have written BKs like this. But if you notice, this can also be written in terms of W4 like this. Okay. Now let us look at D0, D1, D2, D3. And this is the same matrix as before. So I have all the 4 terms here, x0, x1, x2, x3. Okay. Now what I will do is, I will kill these 2 things. I will make them to 0. So this is what I will do. I will kill these 2 things, makes them to 0. So when these 2 things are not there, you can imagine that this column and this column vanishes because these 2 columns doesn't have any role. Okay, so you understand, right? So earlier I had 4 terms, but I am just removing the odd terms because decays are coming because of odd terms. Decays are coming because of even terms, so I have removed the odd terms. When I remove the odd terms, these two columns disappear. These two columns doesn't have any role. Fine. So now if you look at what is this D naught? If you look at D naught, so this multiplies by this and this multiplies by this, right? And this thing is same as what? B naught. D1 is same as B1. You can see for yourself, this thing multiplies by this and this thing multiplies by this, which is exactly B1. So D0, D1, D2, D3 are actually B0, B1, B0, B1. Is this okay? Is this strategy clear?
Yes, sir.
Yes, sir.
Okay. Now similarly, let us see. Now I will go a little bit quick because you have understood this. Now I simply have the odd terms. This and this. And I kill these even terms. And let us see what happens. So when I kill these even terms, of course, these two columns disappear. They do not have any role. And you see E naught is this multiplies by x1 and this multiplies by x3. Okay. Fine. So you see that this is same as C naught. If you look at this C naught. Now let us look at E1. This multiplies by x1 and this multiplies by x3. Is it same as C1? No.
No, sir.
But if you look this carefully, this is W4 1 times C1. Right? E1 is W4 1 times C1. Right?
Yes, sir.
E2. What is E2? E2 is, what is it? W4 2 times C naught. Okay. And E3 is what? W4 3 times C1. Clear?
Yes, sir.
Okay. So what I am saying? I am saying E naught is this, E1 is this, E2 is this, E3 is this. Right? Now the final step. Final step is if you have to calculate E naught, E1, A naught, A1, A2, A3. A naught will be D naught plus E naught, even terms and odd terms. A1 is D1 plus E1, A2 is D2 plus E2, A3 is D3 plus E3, right? And we have seen that this is simply D0, D1, D2, D3. We have seen B0, B1, B0, B1. E0 also we have seen this is like this. Okay. Now let us compute the total number of terms in calculation of this. So how many multiplications are required? If I calculate a case by using this strategy. So first of all, you require some multiplications to calculate B case and C case. How many multiplications we calculated? Just let us see that. Yeah. Total number of multiplications, 8. Let us write it. So total number of multiplications in computing B case and C case, 8. You have to compute B case and C case. Now you also have multiplications here. This is also a multiplication. So 4 multiplications. So if you calculate A case using this strategy, total number of multiplications is 12. Earlier 16. Okay, so we saved in some multiplications. It doesn't seem like a very good saving at this stage, but it is some saving, you will agree. Okay, how many additions? How many additions? So let us come see how many additions we have calculated before. So 8 additions before. So now let us write it 8 additions, and there are how many additions? 4 additions. So total number of additions is 12. So now multiplications 12, additions also 12. No, why do I write 8? Was there maybe 4 additions?
It should be 4, sir.
Yeah, sorry.
Two
This
in each.
total number of additions is 4. Yeah. So total number of additions were 4. Now it is 8. Okay. So now we have got 12 multiplications and 8 additions. Earlier we had 16 multiplications and 12 additions. So there is some saving if you have used this approach.
Excuse me, sir.
Yeah.
So we have 4 additions here also, right? When we calculate A0, A1, A2, A3.
Yeah, 4 additions. This I have counted.
Oh, okay.
And 4 before 8. Okay.
Yeah, okay, sir. Okay.
Now let us look at total number of savings. It doesn't seem like you are saving, you are reducing the number of multiplications from 16 to 12. Doesn't seem like a good saving. But let us see what is the total number of multiplication steps in computing n-point FFT. Okay. So to look at that, so we are just focusing on multiplication. So suppose I have to calculate M2, 2-point FFT. So what is the strategy? I have to first compute M1. M1 means I am breaking down this n length sequence into 2 sequences of n by 2. Right? And for each this n by 2 sequence, I have to compute FFT. So let us assume that the number of steps in computing n by 2 FFT is M1 if my n is 2. And I have to do this 2 times because I have to compute FFTs twice, B case and C case, right? So there has to be a factor of 2. Now, of course, if it is a 2-point, so there has to be 2 multiplications. For example, here, if you look at this picture, because this was 4-point, so there were 4 multiplications. Similarly, if there was 2-point, there would be 2 multiplications. So M2, I can compute it like this. Okay. So now, after having understood this M1, if there is only a single point FFT, then there is no multiplication. And this is simple 0. M2 is 2 times M1 plus 2. So if I substitute this, this is 2. M4 is 2 times M2 plus 4. You will see that this is 8. Similarly, M8 is 24. If you go on like this, you will see that Mn is n log 2 n. So the total number of steps in n-point FFT multiplication steps is n log 2n. Whereas earlier, how many steps were there? N square. So we have converted n square into n log 2n. So there is a lot of saving. For example, if my n is 1024, then in original you have to do so many steps. I don't know how many, 10,48,576. But if you use this approach of FFT, then we can just do this in 10,000 steps. So 1 million operations reduces to 10,000 operations. So a lot of saving in terms of speed and things like this. Okay, understood FFT?
Yes, sir.
Yes.
And this is not just this is not only one algorithm in FFT. You can do FFT using many algorithms. The algorithm that we have presented is divide and conquer algorithm. Okay, and this divide and conquer algorithm is proposed by these two great men, Cooley and Tukey. They have published it as a research paper. You can read about their research paper. They published their work in 1965, so quite old work. And they were working at IBM. And as I have already explained, this is the most used algorithm in the world at the moment. And they developed this FFT because of a different work altogether. So they were having problems in computing DFT because they had a lot of sensors which were planted to detect nuclear explosions. So they had a lot of sensors and they were getting data from a lot of sensors. So N for them was very large, and when they were doing this using DFT, they had some issues. It was just not a scalable thing. So then they realized that there has to be some algorithm which reduces these number of operations, and for that purpose they have developed this fast Fourier transform. Okay.
Sir, could you go back to the slide where we split AK into BK and DK?
AK into DK and EK. Yeah, this one.
Oh, yeah, fine. I thought you split it into something like BK and DK. It's fine, sir.
Yeah. Okay, so now let us change our mode. So from fast Fourier transform, we are going back into Fourier transforms. So let us first answer a few basic questions. If you have a picket fence, I like this word and that's why I use it. Picket fence means impulse train of impulses. Okay, this is a train of impulses where each impulse is located at a period capital T. And this is the expression, mathematical way to write a picket fence. What is the Fourier transform of this picket fence? You must now know this. This is just a recap of the important concepts. What is the Fourier transform of a picket fence?
So AK equals to 1 by T.
I'm talking about Fourier transform. AK 1 by T is a line spectrum. I'm talking about Fourier transform. CTFT. You were correct. So if I have to look at the line spectrum, so I want your 100% attention because this is really the basic. And you will see some very beautiful things emerging out of it. Just wait for a few minutes. So line spectrum of this picket fence, we have seen line spectrum, that means A case is this. So it's 1 by T, the amplitudes is 1 by T, and then you have these lines appearing after 2 pi by T. Okay. Now, how do we convert this line spectrum into Fourier transform? This is a periodic thing, right? How do we convert this line spectrum into Fourier transform? How we go from Fourier series to Fourier transform spectrum?
So take it in a one period of time. So just just 0 to n. So I think n is 1 here, 0 to n minus 1.
No, you're getting too much confused. I think these things must be clear. So if you look at, I will do it quickly. We have discussed this already. Suppose my xt is a periodic signal, and any periodic signal I can write it like this. Right? What is the Fourier transform of this expression? We have seen that the Fourier transform of this expression, you have to look at the lectures again, is this. Fourier transform of this expression is this. What does this mean? Now you have impulses. So you have impulses. These are impulses in place of lines. So earlier we had lines. Now we will have impulses in place of these lines. And what is the weight of these impulses? 2 pi AKs. That's it. So it's very easy to convert a line spectrum into Fourier transform. What is the strategy? Wherever there was line, we just replace this line with an impulse. I don't think you are doing your tutorials in a very good way. And the weights of these impulses is 2 pi AKs. AK here is 1 by T. You have understood converting line spectrum into Fourier transform. Wherever there was a line, you replace that line with an impulse. Weight of these impulses is 2 pi AKs. So because my AK is 1 by T, the weights of these impulses will be 2 pi by T. Clear?
Yes, sir.
This is the way how you convert a line spectrum into Fourier transform. So if I look at the Fourier transform of this signal, Fourier transform of this signal is this. So these impulses are separated by 2 pi by T, and the impulses has a weight of 2 pi by T. So what you can say, what is the Fourier transform of a picket fence? Is another picket fence. Fourier transform of a picket fence is another picket fence. Remember, this is a very useful result. Okay, we can say the Fourier transform of a picket fence is a picket fence. And how can I represent this picket fence mathematically? The weights is 2 pi by T, and these impulses, so these are impulses. These impulses are separated at 2 pi by T. Is this okay?
Yes, sir.
Picket fence has a Fourier transform, which is a picket fence. It's a very, very good, right? It is one of the few signal which has the Fourier transform of the same form as the original signal. What is the another signal which has the Fourier transform of the same form as itself? Fourier transform of Gaussian signal, Gaussian function, is also a Gaussian function. Fourier transform of picket fence is also a picket fence. I think this question was also in a tute. Anyways, this is not so important. This is very important. Once you have understood this, let us look at the relationships between Fourier transforms. So we have done a lot of Fourier transforms, 4 Fourier transforms and series. And now let us try to put them together, try to see what is the relationship between each of them. So let us look at CTFT, continuous time Fourier transform. Continuous time Fourier transform, just reminding you, you have a periodic signal, right? And a continuous time signal, something like this. So if I have to find the relationship between CTFT and let us say CTFS, continuous time Fourier series, Fourier transform, Fourier series. How can we go from CTFT to CTFS? For CTFS, you should remember that we have a periodic signal, right? Fourier series. In series, we have a periodic signal. The time domain signal is periodic. CTFT, we have the time domain signal aperiodic. So if you want to go from CTFT to CTFS, what should we do? We should convert this aperiodic signal into periodic signal. Okay, so just understand. Suppose we have aperiodic signal. If you calculate this transform, this will be CTFT. Now, if you can convert this aperiodic signal into periodic signal, we go into the domain of CTFS, right? So how do you convert aperiodic signal into periodic signal? This strategy is known as periodic extension. You have an aperiodic signal, and by periodic extension, you convert this into periodic signal. Okay, so once you do periodic extension of your signal, you are going from CTFT to CTFS. Understood? Yes or
Yes.
no? Okay. So now the question is, how do we do periodic extension? Suppose you have this aperiodic signal. How can you convert this into a periodic signal? Tell me, how can we convert this aperiodic signal into periodic signal?
Sir, we'll repeat this triangular signal in the region where it is defined.
Yes, exactly. We have to repeat this. So you have a single cap. I call this as a cap. You have a single cap and you repeat these caps. Right? That's what you have to do. You have to put these caps at the integer multiples of capital T and will make it periodic. And mathematically, how you would do it? Mathematically, we can do this by convolving convolution with the impulse train, where impulses are separated by capital T. So if you do convolution between this signal, it's a periodic signal, and this signal, what is the answer? The answer is this. You put this cap wherever there was an impulse. So you take this cap, you put it at this location of impulse, you get it. You put this cap at the location of this impulse, you get this. You put this cap at the location of this impulse, you get this, and so on and so forth. So because my impulse, it's a train, it's a periodic thing, so this also becomes periodic. So how do we do periodic extension? Answer is very simple. We convolve this with an impulse train. And we can obviously decide the period, the time period of the periodic signal by choosing the time period of the impulse train. Clear? I hope so.
Yes, sir.
It's very simple. Now let us look at its Fourier transform. What happens in the Fourier transform? So I have taken a signal convolving with an impulse train. In Fourier transform domain, it will be a multiplication. Convolution in time domain leads to multiplication in frequency domain. So instead of convolution, first is multiplication. Multiplication of what? Multiplication of the Fourier transform of this, which is, let's say, signal like this. Anyway, what is the Fourier transform of a triangle function? What is the Fourier transform of a triangle function? Are you attending tunes?
Yes, sir.
You don't know the Fourier transform of a triangle function? How can I think about a triangle? If you take two rectangles, right? If you convolve them, we will get a triangle. See for yourself. I'm just giving you some quick insight. So I get a triangle by convolving two rectangles. So the Fourier transform of a triangle is multiplication of two sinks. So Fourier transform of a triangle function is sink square. Okay, see for yourself this. I get a triangle by convolving two rectangles. Convolution is multiplication in frequency domain. The rectangle has a Fourier transform sink. So Fourier transform of a triangle is sink square. You can look at this idea, discuss with TAs, and you should know what is the Fourier transform of a triangle sink square. So the triangle has a Fourier transform sink square. Convolution becomes multiplication. Picket fence. This is a picket fence, has a transform which is a picket fence. What is the weights of these impulses? 2 pi by t. Right? We have already discussed this, and these impulses are separated by 2 pi by t. So if you multiply this transform with this picket fence, what will happen? Multiplication. You will get a discrete spectrum. Right? Multiplication, because this is discrete, my spectrum will become discrete. Okay. So moral of the story is, what is the story? Whenever my periodic signal whenever we have a periodic signal, this periodic signal can be thought as convolution of a periodic signal with impulse train. That means in frequency domain, this will lead to the discretization of the original spectrum. Because in Fourier domain, it is multiplication of the original spectrum with an impulse train, which will lead to the discretization of the spectrum. Okay, clear? So
Yes.
that's why when we are looking at periodic signals, so CTFS is about periodic signals, and its spectrum is always discrete. There is a reason for this. The spectrum of a periodic signal is always discrete. And what is the reason? Because in Fourier domain, it is the multiplication with an impulse train. Okay, impulse train is discrete, so whatever you get is discrete. Okay. So if I have to go from CTFS to CTFT, what should we do? We can come from CTFT to CTFS by periodic extension. From CTFS to CTFT, what should we do? We should increase the time to infinity. The time period of this signal should be increased to infinity, and you can relate yourself that this will make the spectrum smooth. Why? Because the impulses here, the impulses which were separated at 2 pi by t will become a continuous thing, right? Because t tends to infinity, and so this spectrum will become continuous. Now from CTFT to DTFT, what is the relationship? CTFT to DTFT. How can you go from CTFT to DTFT? So you have a continuous signal here, right? And here the signal is discrete. So if I sample my continuous signal, right, I can go to DTFT. So going from CTFT to DTFT is easy. You have to do sampling. How will you come back from DTFT to CTFT? We have to do interpolation. We haven't still seen interpolation, and there are some lectures dedicated to sampling and interpolation. I think 2-3 lectures we will talk about sampling and interpolation. So I'm not covering everything that is there in sampling and interpolation. I'm just giving you some ideas today. And then we will build upon those ideas. So the strategy to go from CTFT to DTFT is sampling, and coming back is interpolation. So what is sampling? What is sampling? Sampling means you have a continuous time signal. Let us say signal like this. What is sampling? We multiply this with impulse train. That's what sampling is. Right? You have a CT, continuous time signal, multiply this with impulse train. When we multiply this with impulse train, my signal will become discrete. Okay. Okay. So in frequency domain, what would happen? Let us assume that this is Fourier transform. So let us assume that this is the Fourier transform of this signal. So in frequency domain, we will convolve multiplication. Frequency domain, we will convolve this with an impulse train. Okay. We have the original spectrum convolved with an impulse train. Again, the weights of the impulses is 2 pi by t. The separation between impulses is 2 pi by t. Fine. What will this lead to? This will lead to this cap again coming at these various impulses convolution. So what would happen is, if you take a spectrum like this, its Fourier transform will be like this. So let me repeat. You have an original signal. We multiply this with an impulse train. We get a spectrum like this. Now in frequency domain, what would happen? We have got a spectrum convolved with an impulse train. We will get such a spectrum. That means if you have a signal like this, the Fourier transform of this will be this. Now this is a periodic signal. You see, this is a periodic signal. So that's why, what is the moral of this story? Whenever we discretize a signal in time domain, its spectrum becomes periodic. And again, repeat all the steps in your head. Sampling, multiplication with impulse train. Spectrum, convolving with impulse train. Spectrum becoming periodic. You have to close your eyes and repeat these steps several times so that you get always a firm picture about this. Now, let me repeat some of the steps. Xt has a spectrum. Let us assume that it has got a spectrum x cap omega. Let us say the spectrum of xt is x cap omega, which is like this. Now, first step is we have multiplied this with an impulse train. Mathematically, this is like this. And its spectrum will become periodic because this thing will get convolved with an impulse train, convolution with an impulse train. You will get this. Okay, work this out yourself clearly with some patience and you will see this. So what I am doing is x cap omega getting convolved with 2 pi by t summation del omega minus k 2 pi by t. You should work this out. And when we multiply two signals in time domain, there is 1 by 2 pi factor also. Okay. So this signal has this spectrum. Okay. You will see that the result of this is simply this. Right. But we have, this is still continuous time signal in the sense that I'm writing this in terms of Dirac delta, which is an impulse function. It's a continuous time. So I can convert this signal into a discrete signal xn. I'm looking at discrete time signal. I can convert this signal into a discrete time signal xn if I simply store the weights of these impulses. So xnt is the weights of these impulses. So if I convert this signal into this signal in form of lines, so there are no impulses anymore. And what does this line represent? This represents the weights of these impulses, x and t. And let us say this signal has a spectrum which is xej omega, discrete time spectrum. Okay. So how do we get to a pure discrete time signal? First, we take a continuous time signal, multiply with the impulse train. And then in the discrete time signal, we store the weights of those impulses. Then we get a pure discrete time signal. And that pure discrete time signal, let us say, has a spectrum xej omega. This signal has a spectrum x omega. Okay. So I'm asking you now a question. Is there a relationship between xej omega and this x omega? Is there a relationship? There is a relationship between this xej omega and this x omega. They are not independent of each other. Okay, let us see that relationship now. Very carefully. X omega is by definition this, right? X dt is the discrete time signal, this one, this signal, whatever is this, I call this as x dt. So x omega is the Fourier transform of this x dt. By definition, it should be something like this. Now I write x dt, which is this signal. Right? Instead of using k, I can also use n. Okay. Fine. So instead of xkt, you know what is xkt? I can also write this as xnt. And this is nothing but xn. Right? Okay. So this is xn multiplied by what? Delta t minus nt. This signal is same as this signal. Summation. Everything remains same. Now I can swap this summation and integration. I can pull this summation here. I can have xn here. I can have this integration here. Without worrying about whether this is true or not, let us assume this to be true. Now this thing e to the power minus j omega t, this takes a value only at t equals to nt, this one. And when it takes these values, this is not a function of time, so this could also be pulled out like here. And then we have only this summation, this impulse remaining inside this integration, and this integrates to 1. So x omega is simply this. And you can see by definition, this thing we know by definition what it is. It is xej omega, where this capital omega takes the value little omega times t, capital T. Right? So xej omega by definition what it is, xn e to the power minus j omega n. If you put this omega as capital this little omega times t, so this, if I put omega as little omega times t, Then this is xn e to the power minus j n omega t, which is exactly what you have here. So this xej omega, when omega is capital Omega is little omega times t, is simply x omega. Okay. What is the meaning? Meaning is, if the Fourier transform of this signal is like this, we have already seen this Fourier transform. This becomes periodic, right? Period is 2 pi by t and so on and so forth. This is x omega. And this is plotted versus omega. Now, if you just store the weights of these impulses, and if you want to calculate its Fourier transform is given by xej omega. And we are plotting this versus omega. What should we do? Omega is this omega times t. So the 0 transposed to 0, this 2 pi by t is transposed to 2 pi, 4 pi by t transposed to 4 pi, 6 pi by t transposed to 6 pi, and so on and so forth. Because we have to multiply this omega with t. That's it. So what you see here, xej omega becomes periodic with 2 pi. And we have seen that also. Okay. So in some sense, all these Fourier transforms are interrelated. If you start with one, you can always end up with the other. Fine. Last slide. What happens if I go to DTFS from DTFT? We have seen how to go from here to here, all the steps. Now, if you want to go to DTFS from DTFT, what should we do? If this has got this transform, we have seen this. If you periodically extend this, then we know intuitively what will happen. Because of periodic extension, whatever spectrum I have originally, this will get discretized. That's it. So this will be the spectrum now. The discrete spectrum. Spectrum is getting discretized. That's it. Periodic extension. Now, if you look at this spectrum and this spectrum, this spectrum, suppose I transmit the or suppose I store this spectrum. This can be stored, right? Because it's a discrete time. This can be stored. Discrete time I can store it. But you cannot store this. Cannot be stored. Because this is continuous frequency, cannot be stored. We can store this. The only difference, once you store this, the only thing this continuity tells, the only thing that this continuity tells here is that this thing is not repeated here. What I am trying to say is, if you store this spectrum, you have every information about the original signal. Nothing is lost. If I simply store xej omega, that means if I store this xej omega at discrete points, if I sample this xej omega at discrete points, then I can store this. Does this stored signal has every information about this signal? Yes, it has. It has. This stored signal has all the information about this original signal. No information is lost, if you see clearly. Okay. So there is this idea that you, yeah.
So let's say here the signal we have is in a small period of time, right? It is present. But what if it is present for a long period of time? So when we convolve with some delta, it won't simply repeat. We'll have some other formations too, right?
Yes, exactly. Yeah, your question is very correct. And there are some complications or some strategies that we have to use in discretizing the signal properly. Okay, so all those issues we will see how to do sampling of a signal properly when we do sampling. At this moment, I am not talking about those issues. I am saying just this, let us treat it as motivational. If you somehow discretize this properly, okay, let us use this word properly. Then in this discretized sample, you have every information about this signal. And that's what you want. So actually, which transform is the most used one? DFT or DTFS. DTFS is most used because its spectrum is discrete. You can store this, and the original signal is also discrete. Okay. And even if you want to take its Fourier transform, you don't do DTFT, but you do DTFS. You treat this as a periodic signal, something like this, and you take its DTFS, you get the spectrum like this, and you can store it because in this stored spectrum, you have all the information about this signal. Of course, you have to do this carefully. And we need to have some knowledge when we can do this and when we cannot. So I stop this lecture with this two important points. That's why DFT is the only practical thing to be useful. This is not practical. You cannot store this in computers, right? So this is not useful. And FFT is the most used computer algorithm. So I stop here and see you on Tuesday. Thank you so much.